Hello mathematicians, I am Annalakshmi from V.H.N.S.N.College, Virudhunagar. Today we discuss about Cayley's theorem. First we see the statement of Cayley's theorem. Every group G is isomorphic to subgroup of A of S for some appropriate S, where A of S is the set of all 1-1 onto mappings from S into S. That is, every group G is isomorphic to subgroup of A of S. A of S is the collection of, not elements, collection of functions. That function satisfying 1-1 and onto. Okay. Now we see the proof. Let G be a group. Take S equals G. If G belongs to G, take one element from G. Okay. Now we define the function tau G from S into S. Okay. Therefore, tau G of X equals X into G for every X belongs to G. First, our claim is tau G is 1-1. X, Y belongs to G. That is, we take two elements from G. Next, tau G of X equals tau G of Y. This implies Xg equals Yg. This implies X equals Y. We use cancellation law. Therefore, tau G is 1-1. Next claim is tau G is onto. Take one element from G. Since G belongs to G, this implies G inverse belongs to G. We know. Okay. Yg inverse belongs to G. Tau G of Y into G inverse equals Y into G inverse G. Since we already defined the function tau G of X equals Xg. That equals G. G inverse into G equals identity. So we get the element Y. Therefore, for any Y belongs to G, there exists Yg inverse belongs to G, such that tau G of Yg inverse equals Y. Therefore, tau G is onto. Hence, tau G is a bijection on G. Now we prove that tau G is 1-1 and onto. Therefore, tau G is bijection. So, tau G belongs to A of S. That is, A of S is the collection of function which is satisfying 1-1 and onto. Therefore, tau G belongs to A of S. Okay. Now we define psi from G into A of S by psi of G equals tau G. Now our claim is psi is a homomorphism. We take two elements from G. GH belongs to G. Psi of GH equals tau GH. Tau GH of X equals X into GH. That equals Xg into H. So all are groups. So satisfying associative law. So we take the bracket. That equals tau H of Xg. That equals tau G, tau H of X. Therefore, tau G H of X equals tau G into tau H. Okay. Therefore, psi of GH equals tau GH. That equals tau G into tau H. Therefore, this implies psi of G into psi of H. Therefore, psi is a homomorphism. Next, our claim is kernel psi equals singleton E. Why our claim is that one? We see later. Okay. Let G0 belongs to kernel psi. Therefore, psi of G0 equals I, where I is the identity element of A of S. Kernel is meaning that the collection of all identity element in kernel. Which element satisfying that function, that image is identity we take that element belongs to kernel. Okay. Therefore, tau g naught equals I. Therefore, tau g naught of x equals I of x for every x belongs to G. Therefore, x g naught equals x. This implies g naught equals E. Therefore, kernel psi subset of singleton E. Clearly, singleton E subset of kernel psi. That is, kernel is the collection of identity elements. So, singleton E subset of kernel psi. Therefore, kernel psi equals singleton E. We use the corollary, a homomorphism pi of G into G bar with kernel K pi is an isomorphism of G into G bar if and only if K pi equals singleton E. So, our claim, அதாவது kernel psi equals singleton E ஏன் நம்ம ப்ரூவ் பண்ணோம் அப்படின்னு பார்த்தோம் அப்படின்னா இந்த கராலரியை நம்ம யூஸ் பண்ணுறக்காண்டி தான் நம்ம கிளைம் என்ன எடுத்துக்கிட்டோம், kernel psi equals singleton Eயும் அதே மாதிரி psiயை வந்து ஹோமோமார்பிசமும் சொல்லியிருக்கோம். ஓகே, hence psi is an isomorphism of G into A of S. இந்த கராலரியை நம்ம யூஸ் பண்ணி நம்ம டிஃபைன் பண்ண அந்த ஃபங்க்ஷன் ஐசோமார்பிசம் அப்படின்னு சொல்கிறோம். Since G is a group, psi of G is a group which is subgroup of A of S. Hence, psi is an isomorphism of G onto psi of G, which is a subgroup of A of S. Okay, thank you.